There we go. All right, let's just head into the second to last session of this. And what is the last session concerning book chapters, chapter by chapter? So this chapter I had, I wouldn't say an issue with, but I feel as though it set out to prove why generalized linear models are not always the best approach, but then didn't quite make it apparent why McElreath would like other approaches most of the time. So I've tried to fill that in, but I'm not sure that I hit the mark. So today, basically, we're just going to walk through a few examples of models that one can establish, which are neat, scientifically informed, and then we take what we know from scientific theory and put it over into the realm of statistics. And this is just what we're going to do today. We're just going to walk through a few models which are explained in the book as well. And we're just going to walk through what's the model, what's the data, how did we get to the actual model, how does it look when we code it, what can we take away from it? And for that, I think we've got 4 models today, and we'll start with an old friend of ours, which is the model between weight and height. We had this previously in a session months ago now, where we just modeled weight as a product of height, and we just did that as a linear model, nothing else. And now we want to make this a more scientifically inspired model. Again, I just went with the wordage of, hey, Serena, I just went with the wordage of Richard here, even though I still think that purely statistical models are still scientific models. But that's a discussion for another day, I think, and one that we had a few months ago.
Yeah, I think the Cliff Note version is that if you basically do your best to make everything independent, so it's all additive, then you have like a generalized linear model, because the assumption of like the simple linear model framework is that like all of the regression coefficients are additive.
Yeah.
And here you have height and radius multiplied together. So you have messed up your the effect of both is captured in one. And like the dream scenario is, of course, that you basically have both. Like, so for instance, let's say BMI is predictive of something, right? Then you have the problem that since BMI is like height and weight like divided out, you're totally messed up. But if you if you took the log of your 2 predictors, right, then suddenly height and weight are now additive in log space, right? So my thinking is that you should start with a statistical, like a scientifically inspired model. And then you should do your best to like log, transform, like whatever kind of transformation you can make, such that they conform as much as possible to the generalized linear model framework, because like otherwise you just risk it not being able to sample.
Funny enough, what you just said is going to come up in 4 slides. So this is the model we're running with scientifically inspired wise. We've got W, which is weight. We've got K, which is, McElreath describes it as the relation between weight and volume. I would just like to call that density. H is height, R is radius, and P is then just the ratio of radius to height. So R divided by H. Now our model assumes that the weight stems from a log normal distribution, because it has to be positive. There are no negative weights. The median of that weight distribution, the log normal, then is built by multiplying together K, pi, P squared, and height cubed, and we just need some priors for K and P. However, with a keen mind, we of course can set some intuitive priors here, but we'll notice that K and P are unidentifiable, because we can multiply any 2 numbers together to get to a certain outcome. So running this model might just be a bit difficult, unless we have super informative priors. That might help. So how do we prepare our model? In order to prepare our model, we can do a few things. First thing we could do is introduce a new parameter to address the issue of K and P being unidentifiable. The new parameter will introduce just replaces K times P squared, and is now that theta symbol. Now, unfortunately, we don't have an intuitive prior for theta. So we've solved one issue and created another. So let's try to take a step back from that, and let's try to see if we can come up with good priors for P and K. Now, as an intuitive prior for P, remember P is, actually I have to flip back myself. P is the ratio of radius to height. We know that this has to be positive and between 0 and 1. It's a ratio, hence why it's bound between 0 and 1. And we also know that if there's no height, then there's no radius. And if there's no radius, then there's no height. So 0 and 1 can be safely excluded. Now, what we also can say for our prior is that probably
wait, if it was height to ratio, then it would not be bound between 0 and 1, right? It's just because most people are higher than they are like wide. Right, so it's an artifact of human beings being taller than they're wide, right? So
yes, that's
it's more
that's
like we're using the beta as like a fake thing because we know it's like way below 1. We can use that one as a
yeah, and that's coming up now, where P from our assumption has to be smaller than 0.5, because usually a human is taller than they are wide. So now we've got a pretty informative prior for P. Can we set an informative prior for K, which is the density of our human, so the average density of our human? Unfortunately, that's a bit difficult because K is dependent on the measurement units of both weight and height. So what we can do to address this is just simply standardize the variables, which will help us come to an understanding of saying probably at average weight, our human will be of average height, or sorry, of average volume, which will be the density. So what we can do is just put an exponential on this. We know that this must be positive because when there's no volume, there's no weight. And here we're just assuming that so when P is smaller than 0.5, just with the way the model is structured, K has to be bigger than 1. And once we've got all of this, we've got our model. Model up on the right-hand side, just to remind us of what we started with, what the priors are that we've set now. And then on the left-hand side, we just put all of this in GLM code. And I don't think this poses any issues for any one of us. This is just basic GLM code and then the precise output underneath. And we can see that our assumptions of K being greater than 1 holds true given the data and given our model. And we can also see that our assumption of P being smaller than 0.5 also holds true given the data and given the model. So the question comes up again, are K and P truly unidentifiable? Well, we could say that the interval around K is quite rather large. And maybe that's an issue. But before we get into just the numbers themselves, let's just plot the output. So right here, we're just plotting the pairs plot of the two posteriors, K and P. And we can see that they are negatively correlated. And what's important to point out, which our model can't take into account or hasn't taken into account yet, is that K might not be constant and P might not be constant. So for different individuals, if we just think about age, we might end up with different densities for young individuals versus old individuals. We might also end up with different relations to height, to radius, which is P, for different individuals of different age or of different origin. That is thinkable as well. All of this hasn't been factored into the model and probably should be if we're really trying to get to an in-depth understanding of what's happening here.
Quick question, Eric. P
Yes.
was the density, or?
No, P is radius divided by height.
Okay, I'm just wondering where the informative prior is you argued for on the last slide between 0 and 1, the ratio thing.
Right. So, sorry, Jan, you muted. Do you want to take it away?
Yeah. Then so like you have standardized, right? So you have some standard height, and given a standard height, how much of that standard height are you with? And then like it picked beta 218, which is like 20%, right? Or 10%, sorry. So maybe that's too narrow. So it assumes that you're like 10% as wide as you are high. So if you're 2 meters tall, you have like 20 centimeters over your shoulders. And I think that is like way too narrow. I think it should have been like a beta 416 now that I reason about it out loud. No, it's the radius. It's not the diameter. So it's this part, right? That's the
True. Yeah.
And that makes that's fine. That's 10% because then this is 26.
So yeah, the important does that fit with your experience, Bernd?
I'm not sure. I think my thumb to small finger measurement is not really precise, but
we'll just put some measurement error into the model next time. All right, but this leads us into the big question, which came up earlier and which Jan basically already answered for us. And this is, where's the linear model in all of this? And basically, what we see here is this is not a linear model because stuff is not additive. But that's only because we are looking at this in linear space. And as soon as we translate this into log space, suddenly we see the addition. And taking this apart, the formula on the left-hand side, which is what we've used thus far, we can, on the right-hand side, transform this into a just basic GLM approach with an intercept made up of 3 different things, and then the predictor variable of height with this coefficient of 3, or the exponent of 3 on the left-hand side. So basically, a lot of natural relationships are GLM relationships on a specific scale of measurement, in this case, log. Next model that we're running. Now we're talking about hidden minds and observed behavior. So I've just run with the titles for the subsection from the book here. I had a bit of an issue trying to condense all of this down because I didn't have a lecture to work off of. So the example that we're running with here is that children look at some selected color boxes, or children select colored boxes after they've observed 4 other children take some of these boxes. And we can control what these other 4 kids are doing. And we know that in all of these setups, 3 out of the 4 kids that were observed prior to the kid that we want to observe picking a colored box, 3 out of these have picked color A, which I just called aquamarine. 1 has picked the color B, which I just call beige, and no one has picked C, which I call chartreuse. Now, the big question that comes up is, having seen this, how influenced are the kids that then come up after the demonstrators have picked their boxes? How much are the kids that we now observe taking their boxes? How much are they influenced? Sorry, I just keep restarting that sentence. How much are they influenced by the majority choice of color? Do they all just go for the majority choice of color? That's the big question here. Now, in the data set, we have a certain color coding. Color index 1 is chartreuse, the color that none of the demonstrators picked. Color 2 is aquamarine, which is the majority color, and color 3 is beige, which is the minority color. We also have another variable, which is called majority first, where 1, the value 1, indicates that the majority color, aka aquamarine, was drawn first, and 2 indicates that the minority color was drawn first. So drawn first meaning the 4 kids that went into the room that our observed kid observed itself, which box did they pick first? Did they pick the majority box first, or did they pick a minority box first? When we just look at the data itself, we can see that, and this corresponds to the color coding on the left-hand side here, we can see that the color that no demonstrator picked came up the least, so that is this right here, and just around 21% of the cases. The majority color was picked the most in around 45% of cases, and the minority color was picked around 1/3 of the time. And what I mean by majority and minority, I just have to reinforce this because it took me a hot second to get this from the book, is majority and minority just refers to what were the kids demonstrated to see instead of what did they pick afterwards. So there's a disconnect between what they observed and what they chose themselves. And majority and minority just refer to what they observed themselves before picking. And with this, we could already argue, obviously, they're all going with the majority because the majority comes up the most. And that would be a bit naive, just to conclude that all children just pick the majority box here on average because we see the majority coming out as the strongest. The big question we have to ask is what strategies might lead for a kid to select aquamarine or the majority color, to try to explain this distribution of choices of colored boxes. And this is where we have to take a step back from statistics again and just think about the underlying strategies. And here they are. There are 5 strategies which we could consider. One is follow the majority. So you just copy the majority demonstrated color. If you see 3 times aquamarine being picked by other kids, you pick aquamarine yourself. You could also follow the minority. In this case, you will pick the one box, in this case beige, which doesn't show up with the highlighting quite well now that I see this. You could just pick beige because that is the one that the least people picked, and that's it. There's also the maverick choice, where you just choose the color that no demonstrator chose, in this case chartreuse. There's also the random strategy, where you just walk up, you didn't give 2 flying about what the other kids did, and you just pick a box that looks interesting to you. There's one more strategy, which is a bit more intricate and is all about copying the first behavior. So this is about if you saw a majority color being picked first, you will pick majority. If you saw minority color first, you will pick the minority color. And I actually just have to tab out here because I'm now seeing that majority first should equal, so this right here is correct, 1 and 0. And unfortunately, this right here is incorrect, because this right here where I said 2 indicates that beige was demonstrated first should have been 0. I'll just quickly fix that and then resume the screen sharing.
Off by 1 arrow is a heart.
Sorry?
Off by 1 arrow is a heart. There are 2 things that are difficult in programming: naming things and off by 1 arrows.
Yeah, no, it's just I'm just not a fan of indicator variables. I know that we need them to run these models. I just always like to store stuff in my data frames with actual names, but that might just be me. All right, fix that. So the big point here is that each of these strategies, which any one of our kids could follow, comes with a vector of probabilities for each color. So for example, with the first strategy, follow the majority color, the probabilities for each color under that strategy are really just 100% probability for the majority color and 0% probability for everything else. That is given just the hard rule, but there might be some fluctuations around that, and we want our model to resolve these. Now, we can then identify the probabilities of producing the observations for each strategy with Bayes, because we have the vector of probabilities that just hard strategies tell us for each color given each strategy. We can then apply this to our observations and see what the overall probabilities for each strategy are once we've run the model. Just counting, basically. In order to prepare our model, we have to first think about that there has to be a vector of probabilities of each strategy. So basically, there's a vector of probabilities for each color in each strategy, but there's also a vector of probabilities just for all of the strategies. And that's a simplex with five categories in it, because it needs to sum to 1, because you have to use one of these strategies according to our model idea. Of course, there could be additional strategies such as pick the second color that you observe being picked by one of the demonstrators, but we're not considering that here because then we just spiral out of control. Now we need to assign the likelihood of the observation given all of the strategies.
Quick question, like a Dirichlet with like all fours, that actually means that it's like having a beta with like all fours, right? It gives us more options, right? So it's kind of the same as having like an effective sample size of 20. Like so you're fairly sure that they should be uniform. And like I would not at all a priori expect this to be uniform. So I think it's like a very hard prior. Is there any reason for this? Like I didn't read the chapter, sorry.
No, and don't worry about it. I did not see a big reason for that in the chapter either. But yes, I fully agree with you. Without knowing the prize that McElrich set on, I would have probably chosen something that can vary a bit more as well. But philosophically, you could probably also make the argument that you would want to have something somewhat uniform to let the data tell you which direction to go.
No, but like uniform would be all ones. All ones would be that you think anything is equally possible, right?
Yeah.
Just like a beta one is flat.
You don't want completely uniform.
So like when you mean uniform, you mean very close to the same number all the way through.
Yeah. Just what I meant by uniform was everything's more or less equally as likely.
Yeah.
And then we want the data to drive the probabilities for each strategy up or down as it sees fit.
Yeah. So like my intuition would be like if you made up a new strategy, then suddenly all of these probabilities would like that strategy would be collide more with some strategies than other strategies, and therefore they would drive them away from having all the same number. So unless you think you've found all the strategies that would correspond to like them actually being sort of the same number, then like having these very high numbers on all of them seems like ludicrous to me. But maybe it's just my intuition that it's messed up.
No, I see that. I see where you're coming from. But moving on, when we look at the likelihood of the observations given the strategies, basically we just assign, and we actually do this manually on the next slide, we assign a probability of a certain outcome given a strategy. And in this case, we can say that you always, aka probability is 1, observe the majority color, aka yi equals 2, under the majority strategy, which is strategy equals 1. That's just how to read this part, which will prepare us for the next slide. We then just sum all of these together to get an understanding for each observation of where the observation could have originated from in terms of strategy land. The final model then just ends up looking like this, where we just put everything together. Now for the actual model. This is where it gets a bit convoluted, and I thought we might want to take some time to look at a bit of stand code. Now, with this stand code, important things to point out is that each stand model consists of a few things. But before we get into this, I would just quickly like to highlight how we prepare the data so that we know what's behind N and Y and majority first. I think that should be clear by now, and it's just the number of observations. Y is just which color was picked by the child in question for each observation, and majority first just tells us whether the majority color was shown by the demonstrators to be picked first, yes or no. Now for the actual stand model. Stand models contain a few things. The first one is the data block. This is where all of our observed data gets fed into the actual stand model. Right here, we get just 3 integers due to how our data is structured, because these are just integers, numbers without decimal points. First, we get the integer of n, which is just the number of observations in the data. Then we get yn, which is the observed outcome, indexed by n. And then we have the majority first variable, which again has a length of n. Next in our stand model, we get a parameters block. In the parameters block, we put everything that needs to be estimated. In this case, just the simplex for our observed 5 strategies, which should hold the 5 probabilities of our 5 strategies. That's why we say this is simplex, it is of length 5, and we call this P. Now we go into the model block, and this is where stuff ramps up a bit. In the model block, first thing, so we're just going through this line by line by line now to try and come to an understanding of how STAN models work. First, we get a vector of length 5. This holds the probabilities for each strategy in the model itself. We call this phi. This is to be used for each observation. So we iterate over this again and again and again and again and just update it. Then we have the prior for the probabilities of each of our strategies. So in the model block is where we also put our priors. So right here we have our Dirichlet prior, which is just the vector of 5 4s in a row, which we just talked about maybe being a bit too conservative about homogeneity of probabilities. Then we loop over the data. And this is just for this model. It might look different for other models, but this is just to see how we could read STAN code. So we then loop over all of our observations just with an index I. And I goes from 1 in steps of 1 all the way to n, which is the number of observations. This is now where we manually assign the probabilities for each of our colors given the strategies. So what we see now is, and we'll just take one of these lines right now, is if the currently iterated upon color that is chosen, yi, is 2, aka majority color, then we can say that the probability for our first strategy is 1. Because on the majority strategy, we would always pick this color. So on the majority strategy, the probability for this outcome is 1. Otherwise, it is 0. If we don't observe the majority color, we can say that under strategy majority, there's a 0% chance that we will see the majority color being picked. This is just what this one line is doing here that ends on majority. And these 2 forward slashes are just comments in STAN code. So this is what's not executed by STAN and just used for annotation. We can walk through this and just do this for all of our different strategies. Potentially important to point out that for the random strategy, we just always assign 1/3, because on the random, there's always a 1/3 chance that you'll pick whichever color is currently being seen out of 3 colors. And for the majority first strategy, we just take into account the value of the majority first variable. Does that make sense to everyone? I'm seeing a few concerned faces.
It makes sense to me, but so far I don't understand why we don't do all of this as a pre-transformed variable, because it seems to be like the same phi vector, and then you just index it by one of them in the end. But we haven't gone far enough in the model. But this seems all pre-computable.
What do you mean by pre-computable here?
Like phi 4 is always 1/3, right? So actually calculating that every time in the for loop seems silly. And
right, yes, but the important thing here is that so yes, we could just always assign that outside of the loop, no doubt. I think it's just in the for loop for just everything in the same place. I think that's the only reason for this to be here, not necessarily to be as effective as possible. I hope everyone else sees this as well, because phi 4 is just always 1/3. You could just assign this outside of the loop and save yourself the really short millisecond that you need to assign this every single iteration, which of course, if you run really long chains, will build up to measurable slower models. But I think for this example, it's just in this block so that everything's in the same place. Sam, you unmuted yourself as well.
Sorry, Eric, did you say something?
Yeah, you unmuted yourself as well when I asked.
I just wanted to say this was really intuitive, the way that you just described this. I just wanted to say thank you.
Thanks, happy to hear that.
I'm in the mix of labeling vials, so I just wanted to butt in when I can. Just say thank you.
No, absolutely. This took me a while to get, so I'm happy if this helped others as well.
It makes a difference when you talk through the lines. Yeah.
Cool. Next line then. How about it? So on the next line, we then add all of our computed probabilities for each strategy together to the already calculated probabilities for each of the strategies. So this is where phi just gets updated again and again and again and again. This is just the Bayesian updating part of it. We then, last line, compute the marginal log probability where targets.
Wait. There's one thing, like maybe it's moving slow here. So if majority first is 1, then and yi equals 2, then phi 5 equals 1, but also phi 1 equals 1 in that case. So now there's two things that has like 100% probability.
Yes, but these aren't the probabilities of the strategies. These are the probabilities of seeing the currently seen color under each strategy.
Yeah. Yes. Yeah, it's the likelihood thing. So it doesn't have to sum to 1. Yes.
Yes, exactly. And I was right there with you. Like I said, understanding this bit of stand code took me a solid half an hour. Especially the last few lines were terrifyingly difficult for me to get. So I ran into the exact same question. Last line again. This is where we compute the marginal log probability, basically target in stand speak. So that is what's in front of that line of plus equals. Target is just the total log probability in stand speak. And then log sum exp returns the logarithm of the individual probabilities in phi on the probability scale. So that handles the disagreement between log scale and probability scale for us. And this is what updates phi over and over and over again.
That's also super magical that Stan has a variable called target that you have not declared anywhere that you can just magically add to.
Yeah, I have to say it's very unintuitive for me, and I'm not quite sure yet whether I like it or not. But yeah, this is.
I think it's an artifact of this being a very advanced hack your own likelihood function kind of thing.
Yes.
Because usually I haven't seen that many Stan models, but I've never seen the target variable. Because usually you just do like a likelihood line, which is the way your data flows in, just like you do in GLM, right? And then you're done.
Yeah. So this is definitely not the easiest Stan model to get started with, but in effect, we just went full Stan, and we can definitely congratulate ourselves for that. Moving on to the results from this Stan model, because once we run this, we can see how the probabilities for all of our not variables, but for all of our strategies end up looking like. And there seems to be really high favor of our model and the data for the majority strategy to be quite strongly present, as well as the follow first strategy being quite dominant. Random, of course, doesn't really have much of a say because random is very much a catch-all statement for everything that our other strategies don't directly explain. So there's noise in what
I'm guessing, like just think with me slowly here. Random is almost like having like a hierarchical thing, right? Because since any of the 3 other strategies could also be explained by random, it kind of pulls them together because if you have very little minority strategy, it's more likely it's just all random. That's just because if you have 3 times as much minority strategy as majority strategy, you would actually push minority towards 0 because you can explain it by random, right? So it's almost like the reverse of having a hierarchical prior, because it pushes everything away because it could have just as well be explained by random.
Yes, that is what I was referring to by catch-all statement. We're on the exact same page there. So this is also what we refer to as a state space model, where we have multiple hidden strategies which produce our observations, and it is up to us to identify what these hidden strategies might be, because a purely statistical analysis isn't capable of doing that by itself without some thinking on our end and then engineering the analysis to address these different strategies. As a special case, when the states are discrete categories, then we speak of a hidden Markov model. or HMM, just so everyone's heard of it. Now, as far as a GLM approach is concerned, these really do struggle with teasing apart hidden states, because if we don't give them information about potential hidden states, how they're going to get to them. And this is where we now step into the second to last model, which we're going to talk about today, which is called ordinary differential nut cracking, or ODN. The example here is that we look at panda nuts, which doesn't have anything to do with the bear and all to do with just a tree called the panda nut. We now look at primates who have been observed while opening or attempting to open such panda nuts. The response that we want to model is the number of nuts that have been opened by individual primates, where our predictors are age, body mass, and duration of handling of the nuts. Potential questions which we might want to ask would be, if we can see, and spoiler alert, we do see this, primates get better at opening these nuts with age, do they get better as they age because they learn how to open nuts, or do they, so tool use, that is, or do they get better at opening nuts just because they get stronger as they age? And these are questions which we can address with our models. In the next few slides, we're just going to look at, do they get stronger? That's what we're going to look at over the next few slides. So in order to prepare our model, we need to come to terms with the fact that primates, much like everything else, do not grow infinitely big, which, thank God, I don't want to meet a macaque the size of a gorilla. Now, the important thing here is that this is what we're running with. We're running with a differential equation, that's where differential nut cracking came from, where we look at just the maximum mass that our individuals might reach given a certain time, so given a certain age. K in this case, right here in these formulae, is just the rate of mass gain with time. So how much mass do you accumulate with an increase of age by 1? The way these formulae are written is so that we get a decelerating curve that levels off at M max. So you start growing really fast and then you level off as you approach the asymptote of maximum body mass, which is quite biologically sensible behavior. And if anyone disagrees, feel free to jump in. Now we need to also address the relationship between body mass and strength. And what is hypothesized in the book, and I'm very much inclined to go with that explanation as well, is that we actually have increasing returns of body mass. So for increases, basically it's the inverse relationship here to what we've just seen. As in, the stronger you get, the more strength, the heavier you get, the more strength you have. But that relationship gets stronger the heavier you are. So to put this into perspective, if you are tiny or lightweight and you have a 1 kilogram increase in weight, you will have a certain increase in strength, which in this setup isn't as strong as the increase of strength that you get from a 1 kilogram increase if you're already heavy to begin with. And that's because the effect of strength the effect of body mass comes into strength through multiple avenues. One is that a certain portion of that weight can probably be attributed to muscle mass, which directly goes into strength. You could also say that the heavier your limbs, the stronger your impact on the panda nut if you just let your arm drop. In addition to that, you could now also say that the more muscle mass you have, given the increase in weight, the more you can add additional velocity to the impact of your already increased heavy limb.
And the longer your arms are, the longer the moment.
Exactly, which leads to that increasing return of body mass onto strength. So this
like
is the
a
formula
much
we
simpler
use.
argument would be either you're strong enough to open or not, or you're not strong enough, right? And therefore you would imagine it follows like a logistic curve where like at some magical point you're strong enough and then you're in like, I can almost always open them instead of like never. And that will lead you to the same conclusion as this fancy scientific approach.
Yes, you could go with that one too. So this is the formula we're running with here. Well, lambda is just the rate of the opened nuts. Theta has to be greater than 1, as we know. So theta is just the exponent that gives us some understanding of the increasing returns of the increase in body mass onto strength. And alpha right here in this model is just the proportionality of strength to the nut opening. So how much of an impact does strength have onto your chances of opening nuts? In order to get this model, or to get this equation a bit more manageable for our model, what we might want to do is just set m max to 1. Once we've set m max to 1, a few things just nicely factor out here. Basically, we standardize our variable. That's all we're doing here. But with that assumption input into our equation itself, that variables or the weight variable is expressed as m max equals 1, and every subsequent mass value is adherent to that, we can simplify our equation. To simplify this somewhat further, we can take this block of alpha times beta to the power of theta and put that into a new coefficient, which we call phi. And we'll see how all of this comes together on the next slide, where we now look at some prior simulations. Here's our model, and we want to settle on some priors. Even though we don't have a good intuition for phi, potentially we don't have one, I don't have one right off the bat, we can do some prior simulations. And these are the priors we end up on, with these priors being represented in the left-hand side of the plots on the right-hand side, with the rightmost plot showing some other priors. And we'll talk through why we've settled on the one on the left here. First of all, primates mature around the age of 12, meaning as you hit age 12, your body mass should probably level out, or at least start to level out. You can still grow heavier once you've matured, but probably not by as much as when you were juvenile, still aging. And that's why we want to go with those priors on the left-hand side. On the other hand, on the right-hand side, we have this increasing nut opening with age, which is what we expect. However, in the priors on the right-hand side, we do not take into account that we might level off around the age of 12, which is the maturity that we reach. Putting all of this into a model looks like this. Again, this is just simply transferring math stuff into ULAM stuff. And I mean, stop me if you want to talk about this, but I think it's relatively easy to glance over this because we've talked about this for weeks now.
Yeah, so the only thing is like, why do you, I would assume that this would be over dispersed, right? The whole reason we have this complicated model is because we don't fully understand all the huge interaction machines of how monkeys work. And then we assume a Poisson distribution, which has like, dispersion equals mean. Like I would think like negative binomial would be a better fit here. Again,
I completely agree. But I think the important thing to point out here is that we're not after the perfect model right now. We're just trying to demonstrate how to get
the simplest model where we can do this trick. Yeah, fair enough. Sorry.
Yes, but no, don't be sorry, because it's important to point out that these models can still be improved. And I completely agree that negative binomial or quasi-Poisson might be much more appropriate here.
What's a quasi-Poisson?
Quasi-Poisson and negative binomial are both the same thing.
Okay, so yeah, okay, perfect.
Yeah. I just like the sound of the word Poisson. All right, here are the results for this. So on the right-hand side, we can see the actual number of nuts opened with the size of the circles, I think identifying how long each individual was observed. So this is not how long each individual spent on opening nuts. This is just how long did we observe each individual and their attempts to open nuts. Once we look at our model on the right-hand side, we can see that the modeled nut opening skill curve actually levels off at age 12, which is what we would expect if age, which drives mass, has the predominant effect of on nut opening through the combination with strength. So there is strong evidence that strength, as identified through body mass, drives the nut opening skill. This does not, you will remember that we started off with two different questions, one about strength through body mass, the other one through knowledge from age. Having found this does not say that there is no impact of knowledge gained through age. We just haven't looked at that one. But the strong evidence was, so these two questions which we asked in the beginning are mutually exclusive. And it's important to highlight that here. So when we develop this model, the important thing going forward is setting aside that negative binomial might be a bit more interesting to look at here, is that some parameters in our model can definitely benefit from the information of individual primates, whereas others just might not. So to think about this, the growth rates might be different for different individuals or different species. So if this data set came from different species, we might probably want to account for species membership when trying to estimate the growth rate for our individuals. We could also just look at the individuals themselves without species identifiers and try to come to an understanding of growth rates for each individual. So that is your mass gain with age. That's the growth rate here. But there are other parameters in the model, such as our scaling parameter phi, which we introduced by substituting alpha times beta to the power of theta. This is a physical feature because it just tells us about the relation between mass to strength, which is probably not a clever thing to model for individuals, but more of a physical parameter in nature than it is an individual identifier. Of course, we could argue until nightfall about whether we should have this be for individuals or not, because some individuals might make use of their body mass in strength better than others. But I think for now, we can all agree that we see that there's an inherent difference between the growth rate, which is much more of an individual property than the scaling parameter between mass and strength. And this is again where we hit a roadblock as far as generalized linear model approaches go, because at least as far as I know, and the books seem to apply so as well, GLMs don't allow for model parameters to vary differently for different observational units. So if, for example, in a GLM, we just put a random intercept in it or a random effect of something, we apply this to every other parameter in the model.
What's a unit in this case? And like, I'm not fully following here. So a unit would be one of the monkeys.
Yes.
And in what way is it that this ODN allows us to have a different scaling? Because like if you have different species, right, then it's easy in the GLM because you can just have a hierarchical model over that. And then there's this species who has this kind of set of scalings and the other set of species which has this. So like, how is it we can do this in this ODN thing and not do it in GLMs? I don't fully get it.
Right. So the important thing is we're not doing this in the ODN right now. But if we move into just straight up stand code, we can tell our model directly that it is absolutely allowed to vary the growth rate depending on individuals, but it's not allowed to vary the scaling parameter phi depending on individuals. And at least ad hoc, I wouldn't know how to tell a GLM to do this.
Yeah, I suck at ODEs, so I wouldn't know how to do it in ODE either.
I don't think we'll get to an example of this, but let's just put that on the list for over the next few months. We'll just see if we can figure out how to do it.
Yeah.
Cool. Last example, and this is where I'm particularly looking at Sam, because now we're talking about population dynamics. Yeah, you. The example here is a time series analysis where we've got records of pelts of different species, these two species being hares and lynx. And what we look at here is just the response of the hare pelts on the right-hand side labeled as lepus, and the predictors being the lynx pelts and the time that has passed since beginning of our record keeping. We can see that there are some nice cycles on the right-hand side, and we want to build a model that can reproduce these cycles, where we can clearly see that the hare cycle of population dynamics obviously drives the lynx population size, or is at least closely linked to them, which is because lynx really like to munch on some hares, and I can't fault them for it. Now, as far as preparing our model is concerned, there are some typical approaches which we have to talk about right quick. First typical approach would just be an autoregressive model, where we just regress the population size at the preceding time step onto the current time step to get to an understanding of how hare populations influence each other through time. We can then, so here we've got explanation of the different parameters. We can then add the predator as a lag variable. So you can say that your current population size of hares is influenced by the hare population size of yesterday, as well as the lynx population of yesterday. We can then even add deeper lags. So we can say yesterday and the day before that for both the hares and the lynx. Important to point out here is that lags farther than one period back make no causal sense. They might be good statistically because they help us explain something, but causally, they should not have any effect because they will always affect what is currently happening in the population through the last lag period and not through themselves from a few periods ago. Another important thing here is that in these autoregressive models,
like everything you said makes sense, right? But if you imagine like some animal which has a gestation period of 2 years, then the actual number of lynx depends on how many there were 2 years ago, because that's how many could be pregnant, and how many are going to eat is of course only relevant for the current. But the spike in levels is predicted by going 2 levels back, right? And if hares has the same thing, just that like if the prey animal actually had like a very long gestation period, then you would actually have sometimes the numbers would go up heavily because they've been pregnant for 2 years, and
yes,
that's independent of the lynx.
But even then, it's just the last population that influences what's happening in the next. Because if let's go with they're pregnant for 2 years.
No, I think I'm saying like the number of 2 years predicts how large a percentage of them are pregnant right now, and whether they're pregnant right now or not actually determines like how many they're going to be in next iteration.
Sorry, you'll have to break that apart again because you've lost me now.
Okay, so let's say that if the number 2 years ago was super high, then
Yes.
you can kind of infer that right now that they're less than halfway through the gestation. So in next period there'll be very few, because like it's a year later that they'll give birth. So therefore,
just take a step back. We're talking about a hypothetical species right now which is pregnant for 2 years.
Yes.
Okay. And so
then
the population size of 2 years ago should tell us.
Yeah, if it spiked a lot 2 years ago, then probably a lot of them gave birth 2 years. So it's weak evidence that less than average of them are going to be pregnant right now because they're only 1 year old.
Now I see what you mean, but I think this is going into, and Sam, this is where I'm looking at you, because this is going into age class models, which we're not looking at here, because that kind of inference is much better suited for age structured models, because we're right now we're not modeling how many of them are pregnant, we're just modeling how many are there.
But I'm pretty sure like how many that are pregnant like heavily influences how many there are in the near future.
Oh, no doubt. But you will find that how many are pregnant 2 years ago will influence how many are here today, much less so than how many were pregnant yesterday.
Say that again.
So pregnant animals in that 2-year time span might die. So the number of pregnant animals from yesterday will tell us much more about how many animals are there today than how many animals were pregnant 2 years ago.
Obviously, but you don't have the pregnancy variable. So the only thing that could leak that information is like the collapse or the rise.
Yes.
And that you have to go back to the whole gestation period to estimate.
And I would disagree with that.
Okay.
Because they so just the way biological systems work, they don't all get pregnant at the exact same time.
No, of course not.
At the exact same time. So you will see that gradual rise in births, which will lead to a gradual rise in the population size.
But like, okay, so counter argument, right? If when the lynx, like first of all, I'm assuming lynx do not eat average hares. They eat slow hares, so maybe they eat mostly young and old, right? So if like lynx has just like the previous year eaten a lot of rabbits, then there'll be more rabbits that are actually in like a reproductive thing than otherwise, and you could and therefore it could leak through time. But I first of all, I totally agree that if you have these age segregations, it's way better than like my hack, because my hack will only leak like 5% information. Yeah. Like I'm just arguing that potentially you could actually have like a causal reason for going back more than 1 year, and I might be wrong.
In that case, in that case, I think we might be arguing something else. I think what we're arguing then is what's the appropriate lag length which to look at. So if you have species which have extreme cyclicity, let's think of there's
but like
moths,
I take your point, but in a causal inference, the correct lag length is 1 second, right?
Yes,
that's how causality works.
Yes, but if we were to let's take this away from hare and lynx, and let's just talk about moths in Antarctica, because there are moths in Antarctica who are in a larval state for 7 years, and then there's 1 year where they all are moths, and then they go back into larval state. Now, if you're just interested in just the moths themselves without the larval state, you will of course want to have lag length of 8 years each. And I think this is what you're getting at, I think. Just this species is much more extreme. So in this case, we would want to look at 8-year-long lags instead of second ones.
Yeah. Sorry. Yeah, point take.
Cool. But again, really good discussion, and thank you very much for being insistent on your point. So in this case, where we propagate measurement error, especially with trying to propagate something that is badly measured in the right now, trying to explain that through something that was badly measured back when, we have measurement error that just confounds on top of each other. And what we actually might want to run is a state space model. Think back to a few slides ago, we have something hidden, which the model will want to bring back to light again. And this is just the true observations. So this is just modeling with measurement error. Usually, it gets worse with these autoregressive models. We lack some sensible interpretation of the parameters. Like previous time step hare population has a 0.5 influence on right now hare population. It's a bit difficult to interpret. And so we want to do better.
Like, okay, so okay, now I'm just gonna be wrong again. So like the way I would read the one without deeper stuff model, like it's basically like every like beta 1 is how many kids every hare gets per year, and beta 2 is how many hares every lynx eats, right? So if beta 2 is 1, then every lynx eats hare, and if beta is 1, then every hare gets a kid.
But what is alpha then?
Alpha is like the magical is like how something with like when there's a lot they can't hide or something. I took a pointing.
No, I fully see your explanation of the betas was on point, and it was a admittedly bad example for me to hone in on beta.
So alpha is the fact that like if there's only one hare and one lynx, they're not going to find each other.
Yeah. Also, alpha is just bit useless because what's happening when you're at the first time step? Just everything falls apart because you don't have any lag. So we want to do better. How can we do better? We could just use some differential equations again. And we could start with a differential equation that just tells us about the change in hair population with one time step, which has some effect of underlying hair population, which we start with, which then just gets times with the birth rate, and we subtract from that the death rate. To develop this a bit further, we could just make the birth rate and the death rate constant, which, as any biologist will tell you, is probably not the best way to go. But again, we're just not looking for the perfect model here, we're just looking for a model to see how we can arrive at conclusions. So for now, let's just say we make the birth rate and the death rate constant for our hair population. AKA, each year we add 30% of the previous year's population, but we also take away 30% of the population through death, which would be completely balanced, which in this case it isn't, because we do have some predator effects, but let's not think about that for now. We could then make the death rate of hares dependent on lynx. We could also make the birth rate of lynx dependent on the hares, because the more the lynx can eat, the more they will procreate. And we could also probably make the mortality rate of lynx dependent on hare population, because less lynx will starve. But this is all going a bit far, and it's just important to point out that these are just ordinary differential equations again, but they're not quite that ordinary because they have a special name, as in Lotka-Volterra. And most biologists will have heard of this at some point. Serena, seeing how you're not a biologist, you might not have heard of these. These are just a big class.
I'm a biochemist, so I haven't heard of them either.
Oh, thank you for pointing that out, Jan. So for both of you, and Sam, please correct me on that, because I know you are much more in tune with these. From my understanding, Lotka-Volterra models are simply just prey-predator differential equations. It's just, there was a guy named Lotka-Volterra who came up with this for prey and predator stuff. And ever since then, that's just what stuck.
It was two guys.
Named Lotka and Volterra.
Yeah.
There we go. Thank you very much for the correction. Problem with this is that, given that these are differential equations, we don't have explicit solutions for the hare population at time t and the lynx population at time t, because we always need some initial population from which to start solving our equations. We always need to initialize our models with something to get to a certain understanding of where our population will be right now. These models, nice they may be, won't help us to understand what the hare population right now is outside my window if I don't have an understanding of where it started a few years ago, and I can then track it through time. But we can
one year should suffice, right? You just need the delta, right?
Yes. Of course, the more data you have, the better, but you just need at least 2 points for which to start, so that you can then start extrapolating. You probably should trust that model, but just statistically speaking, trying to get your model to compile, you need at least 2 data points. We can combine all of these different equations into one big boy, which tells us about how we can track hare populations going one step at a time. And we can then solve all of this through simulation. So how do we do this? We prepare our model. We need some priors for our observed animal abundances.
When you say solved by simulation, you just mean the normal no U-turn sample trick, right?
Yes.
Okay, perfect.
Yes. So we, first of all, need to model the population dynamics as well as the measurement error. So we need some priors for observed animal abundances. That's the ones we have. Right here, we've got a log normal distribution for both the observed hare pelts and the observed lynx pelts. I will just refer to these as populations and not as pelts. where log pH HT is just the median of the observed hair abundance. And unfortunately, we don't have any good way of estimating that pH parameter. However, we can at least define a few things for our unobserved variables. Right here, again, the explanations on the left-hand side just talk about the hairs instead of the links as well, because let's not make this more complicated than it already is. We just set a prior for the true hair population at time 1. That's our initialization value, which is H1 and L1 for the links. And we then just push our differential equations, which we just saw on the previous slide, straight into the model. All we have to do. And now we're left with just defining some priors. I previously said that we have no good way of estimating pH to give us the relationship between the true population size and the measured population size for both hairs and links. And right here, the book just goes with a very informative prior, and that's all I can say about that. Unless we know the value for P, we don't have a good way of or have a good way of estimating it. We can only identify relative species abundances instead of exact numbers. And that's just a shortcoming of having to deal with measurement error.
There's a lot of things I don't get here. So first of all, so HT is like the real number of hairs, right? And LT is like, not the real, the observed number of links, right? And then this pH is the, like, multiplied by this, and then you have like measurement error taken into account. So it's like some distribution, we just crush into it to get like some uncertainty. But
pH, sorry, I think I know where you're headed with this. pH basically just tells us about the probability of observing the hairs. So basically this tells us out of the true hair population, capital HT, we see just 70%. Because the others are just in hiding. And pH tries to correct for that.
Okay. But like, okay, that's pretty cool. The only thing I have a hard time, like there must be some, like it's really hard to say, were there twice as many links or do they eat half as many hairs, right? That seems
yes. These models are, you're pointing this out beautifully. These models are terribly uncertain of what's happening. And as we'll see in just a few slides, they don't do a terrific job. And that is one of the reasons, because there's a certain sense of unidentifiability going on here. Can I move on? All right, I see some nodding. Now we code our model again. And here we have another stand model, which is a bit more complicated than the previous one. I will not point out all of the base building blocks that we already talked about, because then I'd run out of highlight colors. I am just going to quickly point out all of the important new things that we've added to this model. Now, the first thing we've added is the functions block. In this functions block, we define calculations that we can then use in the model. And in this case, all that we've done here in this functions block is we've added a function which we call dpop underscore dt, which is just the differential equations. Right here. These are the differential equations that we just talked about on the previous few slides. And we need to tell the model how to run these so that it can get the time variable from us. It gets the initial state of the population, pop underscore init, as well as the parameters of our model, which is birth rate, death rate for hairs and links, respectively. And then returns the change of population to us, which is dh dt and dl dt. That's all it's doing. Here we're telling it what it gets in terms of information. And here we're telling it what to do with it. And here we're telling it what to give back to us. If you've coded functions in R, I think this will look very familiar. At least to me it does. And if I'm going too quick, please do interrupt me and we'll talk about this.
Yeah, I'll add some words, like, because the first time I saw this, I was like thoroughly confused. And like the first thing is like, if you're not like a wizard of ordinary differential equations, it's nice to just remind yourself that when you do this integral, then like if you could just do the integral, then the resulting function is a function where if you put in hairs and links, you get back how many of these animals would be at the next time step, right? That's the function we want, but that's not the function we can describe. We can only describe like how they change over time, right? But by doing this magical integral, we get the function we want, right? And now, because Stan is nice in a like convoluted way, because there's still a lot of code, we tell it like this is the relationship like of the differential equation. And then we use this integrate underscore ODE underscore RK45 magical method to get the integral. So now we have the function that can just return the numbers, because then we can stuff that one into the model.
Exactly. This is where the next speciality of this code comes in. The thing that you just pointed out, the integrate underscore OD underscore RK45, which is Stan's very unfortunately named way of integrating the functions which we wrote into the functions block into our actual model. We have put this into the transformed parameters block so that our output appears in the posterior. So if we want to do extra calculations in our model that we want to be tracked in the posterior, then we need to just put it into the transformed parameters block or in the generated quantities block. I think both of them do that function. But if you want to take parameters which you'll model a bit more, then you'll want to use the transform parameters block, I think. I'm not quite certain of the difference between the transform parameters block and the generated quantities block.
I think, and I'm also uncertain here, that transform parameters is like kind of before the model. So that's like this is the stuff that is nice to know, and generated quantities are after the model, right? So you do all of the like if you have like a Bayesian model, you have all the prior stuff, right? And transform parameters are kind of like prior stuff. So it's stuff we do before we run the model. Then we have the model, so we draw some parameters, and then from those parameters we can generate quantities. So I actually think the model is basically run from top to bottom here, and therefore and therefore I don't think you can do this in the generate quantities, because I think that's sampling.
I also just now see what this is actually doing. Because this is just updating the population size, which we're currently looking at, with our actual model later down the road. So yeah, no, you're completely right. This needs to be run before the model. And yeah, with this entire thing, we then get some results, right-hand side. So we've accounted for some measurement error. As soon as we have measurement error, we also have hidden states. The hidden states, which are the true populations at the previous time step, are what actually establish the cause, where the measured states are no causes themselves. And we want to try to reconstruct the true states in the past rather than the measured ones. And modeling time series without measurements induces some bias, because we try to look for causality between things that don't have causality or shouldn't have them. That's the big issue with time series analyses. On the right-hand side, you can see that we're doing a decent job of fitting to the data, although not a perfect one. The big takeaway from me for this very last slide here is that reporting our uncertainties is the key here to really report the honest science about how much we should trust our model. And I am very happy to discuss this, as this is the very last slide that I have prepared for this study group.
And like, so basically what you mean by measurement error are these fake beta things, which are the proportion of stuff we measure, right? Mm-hmm. And you could argue that like one way of actually testing this would be to just delete the last 5 data points and just run it forward, where you keep putting it into itself, right? Because the measurement error version has the advantage that if one of them is unreasonably high compared to the other one, it can attribute it to measurement error and then regress it towards the line.
Yeah. Basically, measurement error allows for the pooling around the time series that we fit.
Yeah, I think this was like pretty great. Like it sucks that Magello didn't have like 3 more lectures just for the curious people.
I honestly, at this point, I wish McElreef would just continue this book and the lectures until I die of old age.
Yeah.
I really like his style.
Yeah. And now the next time you have to do something advanced in Bayesian land, you have to like read an annoying paper that has like logic circuits and like magic stuff nobody understands.
Mm-hmm. No, I will say, given that the last 2 chapters were, I think the last 2 were additions to the book, going from first edition to second edition, I feel as though you can tell because they are a bit much more advanced and less didactically sound, let's say. But I'm sure they'll receive more development and then be much more easy to understand, like the previous ones were.
Yeah, I think chapter 14 is harder than 15 and 16.
Oh yeah, no, chapter 14 just came out of nowhere with how much it ramped the difficulty up. But yeah, I think I'll just do a quick break here, guys, because I definitely need to look at my solutions before I explain them. Resume the recording, and we are good to talk about the solutions to this chapter. For anyone in the call or in the recording who will in the future want to run Stan models from within R through R Markdown to show the code and show the results at the same time, I have now for the second week in a row run into C stack trace errors, which apparently are a common thing with Stan when Stan assigns models to the exact same endpoint on your hard drive, which is usually just an issue if you run base R and you run a Stan model through base R and you save all of your different Stan models to model objects with the exact same name. Now, unfortunately, from what I have gathered, when you execute, even if the models are named differently, so what they're saved to are named differently, if you run them through the knitting process of R Markdown, behind the scenes, everything is still being written to the same endpoint because of R Markdown. So in order to get long R Markdown documents like these to compile with multiple Stan models in there, what I'm doing right now is I'm brute forcing stuff and I'm running the models and then saving the model objects once while I'm running everything through R, where I don't run into any issues. And then upon knitting, I just load all of the model objects in again without showing it to the reader of the R Markdown knitting output so that the knitting actually compiles. But this is more of a, if anyone ever runs into this, now you've heard of this at some point, if you run into C stack trace errors, because this cost me 4 hours last week and another 3 hours yesterday, and it was not cute. But let's talk through the exercises. So thankfully, the PDF version of the book that I'm working with doesn't have any easy exercises included in it, so I just jumped over all of those. There might be some in the print version, there probably are. The book that I'm working with, the PDF, doesn't have any bucket medium exercises it is. First medium exercise asks us to modify the cylinder height model, which we just talked about a few minutes ago, so that the exponent 3 on height is instead now a free parameter, which is to be estimated from the actual data. The question then is, do we recover the value of 3 or not? And we are asked to plot the posterior predictions for the new model and explain how they differ from those of the model in the book. So here's just a quick reminder for those just reading the blog post later on what our model specification looks like. I'm loading the data, I'm rescaling the data to fix the scale dependency of weight and height for our parameter k, which is our density parameter. I then, sorry, I'm just going to zoom in on this a tiny bit because I feel that might have been a bit tiny. We've got the data prepared. We run the model from the book, the exact one that I also presented on the slides. I add logLIC to this so that I can then do model comparison with the WAIC, widely applicable AIC, Ikaike information criterion, just to do more than just comparing posterior predictive distributions. Now, in order to run the actual model that I was asked to run, I simply just assign a free parameter to the exponent 3. So basically, I just replace 3 in my model with a parameter which I call E for exponent. For this parameter, I don't have any good prior. I know that previously we assumed it to be 3. Now I'm just saying it's probably positive, and I just give it an exponential with 1. That's all it is. I run this model again with logLIC set to true, Now, E gets estimated to be 2.33 roughly, rather than 3, as we previously assumed. I'm not actually interpreting this here. This is just an observation. I just wanted to get done with these, I have to admit. In model comparison, our model M1, the one with the free parameter for our exponent, gets assigned all of the weights. So this seems to be doing better in fitting the data. And let's look how it might be better at fitting the data, seeing how model comparison strongly favors our new model. This is where we plot our posterior predictive functions. Left-hand side is the new model, right-hand side is the old model. Let me just quickly make sure that, yes, that is true. And what we can see here is that left-hand side, our new model, that didn't take the exponent to be 3, but now 2.33 as estimated from our precise output up there. We can see that the new model not only has a much narrower uncertainty band, it also has the capability of fitting to short individuals down here much better than the previous model, where we had the fixed exponent. However, we do fit the tall individuals slightly worse than
and the middle individuals especially worse.
True. They are also not being fit that well. But look at the small individuals.
Yeah, but like the small individuals, yeah, is where it thinks it has the smallest error. So that's why we're being off is the most bad, right? It's there's more standard deviations away in the right, right? Because it's like twice as far away from the gray in the right one, right? And there's no one in the left one that is like twice as far away as the gray. And that's why it's better, right?
Yeah. And that was already question M1. Moving on to question M2. Question M2 asks us to conduct a prior predictive simulation for the cylinder height model. We were supposed to begin with the priors in the chapter and then see if these produce reasonable prior height distributions. And if not, which modifications would we suggest? So these are the priors from the chapter. I then just simulate priors. So I simulate 100 priors here with these pre-specifications. I then plot these prior distributions or these prior predictive checks against the actual data. And personally, I'm not happy with these priors. Like, yeah,
but
they are
you're not allowed to
angled.
look at the data when you do prior predictive checks, right? That's
true. I just want to see how much stuff fans out, and to get a nice plotting space, I just put the underlying data on it. But yes, you're right. The priors are not supposed to fit the data.
Because the alternative view is that they're within 2 standard deviations, like or within 3 standard deviations, since you drew 100 times and you have like engulfed all the data. So it's like in pessimist land, they're great. But I take your point.
Yeah, no, the priors are really just supposed to give us some understanding about biological feasibility, or just not necessarily biological feasibility, but just feasibility. Does not just come into play for biological stuff. So these combinations seem a bit too flat. So either P or K being the density and P being radius to height, need to be larger on average for this to just get bumped up a bit. So in order to get our prior lines away from just being stuck directly to the x-axis, I increase my P slightly, and I also alter my exponential function for K. That already looks better. Again, I am not looking to fit the data. I'm just trying to find relationships that seem appropriate to me. Now we've got some prior combinations here of P and K, which are definitely way too extreme, as you can see for this, for example, with very explosive growth between height and weight. but most of the priors, at least from what I can see, still bunch up along the x-axis. So now in this case, I want to alter the prior for k, which is the density, some more, and I want to make it log normal.
Yeah. Can I say, like, when I look at it, like in the left part of the curve, right? I think you have more issues there than in the right part of the curve, because basically,
Yes.
There's only 1 or 2 that are above them in the left part of the curve, but there's like 50 or like whatever the number, 20, 30 that are above them in the right part of the curve. So you need, and I can't remember how these priors work, but you actually need something that lives in that part independent of that part. And I can't, since that's like, now let's think very slowly about this. So you basically need something that lifts weight, that increases weight without increasing height when you pick your next prior.
And that's exactly why I'm altering the density.
Okay.
Because if you're denser, you immediately just jump up a bit. And that's what you can see here. Still, everything needs to start around 0, of course. But these priors look a lot nicer.
Yeah.
And I'm actually happy with these. I also explicitly state here that priors are not about fitting the data, but just informing about plausibility. So, prior predictive simulation, done. Basically just play around with the numbers until you get something that looks right. For practice M3, we were asked to do a prior predictive simulation to investigate the lynx hair model. We were supposed to begin with the priors in the chapter and then asked which population dynamics do these produce? Can we suggest any improvements to the priors on the basis of our simulations? Again, here's just the full model from the book. And the priors in question that we're interested in are these right here. So we just go about.
Let's look at the 4 priors again, just so everybody. So there's the prior on birth rate for both animals and the prior on mortality. Okay, perfect.
Yes. Thanks for stopping me there. We now again just build 100 priors, or select randomly 100 priors from these distributions which we have input into our model.
Like you mean 12, right? Like in.
Oh yeah, 12. Sorry. I was yeah, no. Further down for the plotting, 100 didn't make much sense for how I do the plotting, but yes, 12. Sorry. I just saw a 1 and a 2, and my brain immediately put the E in between the two. Thank you. We just put all of these into one vector, which we call theta, reminiscent of how we did it in the Stan code. Then we use the sim lynx hair function from the book, which just gets fed with a certain number of steps which we're interested in, some initialization, and then our theta priors to try to simulate full-on time series. And I'm just stealing this function from the book because I don't need to reinvent the wheel. And now I simulate
but that function does the integral for us, right?
Yes, exactly. So that just goes step by step by step by step, given the prior that we have of our parameters, and just updates the population given some initialization. And I just initialize with the first numbers in the hair data set. So I just create all of my priors, put them all into one big data frame, and then as I plot them, this is what I get. Hair populations are shown in blue. Lynx populations are shown in, the color is called brown in R, but it looks more reddish to me, I have to say. And personally, I am very unhappy with these priors.
It seems like the lynx can go vegan.
Right? These priors are just not nice, because what we want to see is some cycles. It's fine for a few priors to just shoot off into the ether, but at least some of our priors need to demonstrate the cyclicity of our time series. So how do I propose we alter them? So what could we do better? Let's take them step by step. Let's just look at the hair birth rate, for example. The hair birth rate, BH. I personally just wanted to make this a bit smaller and a bit more a bit more conservative about being small. So I reduced the median amount of hares that get birthed every year, but I made that median more fixed. I thought that hare birth rate was potentially being overestimated by our priors. Now I look at the, sorry, yes?
So I totally get why you take the 0.5 instead of 1, but like, why did you reduce the sigma to like 0.1?
Because I really wanted to make sure that we stay very much below 0.5, below 1. That's why I also just increased the preciseness or decreased the standard deviation.
But like, if you pick like 0.2, you would still be below, right? And 0.25, you would be below in like 95% of the cases.
Yes, 0.1 just looked nice to me. I don't have any numerical answer to this.
Okay, it just seems like a huge step.
Yes, it is a huge step. And this was the end result of me playing around with numbers, finding some nice priors, and then justifying them.
That's a pretty good argument.
So next one that I look at is the prior for the lynx birth rate. This one I just keep as it was previously. I strongly suggest that the birth rate of lynx should be smaller than the birth rate of hares, and this is already established by the previous priors. I just don't think that as many lynx get born each year as there are hares being born.
Like potentially you could actually set it as a transformed parameter of the other one, right?
You could. You absolutely could. Yes. Now onto the mortality. I think that lynx mortality was way too high previously. So lynx mortality previously was, I should have just written this down there. Lynx mortality was half normal with 1 and 0.5. And that just looks as though as many lynx die or lynx die at the same rate as hares are born in the base model. And I just think that doesn't make much sense. So I really wanted to reduce this a lot to reflect that lynx are a much more hardy species than are hares. And also they don't have predators who eat them. They do.
Yeah, like they're indirectly eaten by hares in the sense that they die when there are no hares, right?
Yes, you could make that case.
If you did the opposite regression, right, you could actually come to the, well, they're getting eaten backwards in time, right? But
True. Finally, we've got hare mortality. I here increase the hare mortality to reflect that they die just much quicker than the lynx do. So now in my model, hares get birthed more frequently than lynx, and hares also die more frequently than lynx. And I think that makes good sense biologically. The actual numbers, again, just the result of me playing around with stuff and landing on something that worked for me.
Yeah, but in the order differential equation, there the death rates of hares is predictive of the birth rates of lynx, right?
Yes. Well, it's predicted through the population size of lynx, which is a result of the birth rate of lynx in the previous time step.
Yes. Okay, perfect. And like when you push it through that magic function you didn't write, you just stole from auxiliary. You have that part. Yeah.
Exactly.
Okay.
So again, I do my prior predictive simulation just like I did above, just this time new priors in here, again for 12, and these are much nicer. Again, we have a few that just shoot off into the ether, but I'm honestly fine with those as long as I can see all of the others which actually show some cycles.
Yeah, so the ones that shoot up, like if you take the first one, is that just because you happen to draw a very low number of links, and therefore, like if you actually went further out in time, then eventually the links are going to catch up? Or is it that you're in like this magical world where if there's sufficiently many hares compared to lynx, they can actually outbreed them in this?
I'm not quite sure exactly what's going on in plot 1. It might just be that the lynx population in that plot is just straight on 0. So they might just never come back because there's nothing to come back from.
Okay, yeah. So because like they were unlucky and they drew a larger death rate than birth rate.
Mm-hmm.
And then even though the birth rate is further modulated by the levels of hairs, because hairs also started out low, they died out.
Exactly.
Like and like biologically that makes sense, right? If you have like this is America, there are 3 lynx and 10 hares. Then the 3 lynx are not going to find the 10 hares, so they're going to die out, and then the rabbits are.
Yeah. And even more drastic probably in plot 5 right here, where lynx just abruptly disappeared and hares just shot off. But yeah, just to point out, I think these priors much more sensible. Moving on to the hard exercises. With question H1, we were supposed to go back to the panda nut cracking or opening model, and we were supposed to alter it such that the male and female chimpanzees have different maximum adult body mass. So try to account for different sexes. What we talked about previously, that we want certain things to be influenced by sex and others not to be influenced by sex. Or individuals is what we talked about earlier, or species. Now it's sex. So again, this is just the model from the book. And then I just load the data. And now we would like to think about how we can add our maleness index to this model. And to alter this, what we can do is, and I just have to read this out myself again, is supposed to come through the effective body mass, and the effective body mass is contained within this phi factor right here. This just tells us the relation of body mass onto strength. So this is where we need to tackle the issue. So I thought, why not just add a parameter for maleness, which gets multiplied with the index of maleness, which is just an index of 1 or 0, and it's 1 if the individual is male, and try to multiply that with our scaling factor to show that males have a higher body mass, ergo they also have a higher strength because of the increasing returns. Now with the stand model, I do exactly what I set out to do down here.
Wait, I have one question.
Yes.
From the lecture you gave, the 1 was actually because you set that to the maximum thing, right? And if you a priori just believe that one of the sexes is smaller than the other one, and you a priori believe that one is the female one, then couldn't you have like some scaling parameter on that 1, such that it doesn't affect? I
could have also put that there. True. That's a good point. Yes, I could have also altered this right here.
Because you scale both of them. You scale both the 1 and the EXP, blah blah blah. And like I'm assuming that you only expect it actually to reduce. Like you basically you shift the whole curve, right? Because you basically shrink the whole curve by some factor. And what you want is you just want to shrink the top point, that it converges towards another point, right?
I'm not quite sure I follow on that one.
I might also just be saying wrong, but like conceptually, this 1 minus EXP, that's a whole sigmoid curve, right? And if like by multiplying that by 0.8, you're just shrinking the whole curve by a factor of 0.8, and that might be the correct thing. But I actually think that's the correct thing, and that's what you do. Yeah, because what I'm proposing is that you're shrinking the 1, and that's super wrong, right? Because then if you shrink the 1 to like 0.8, that's the same as actually adding 0.2. So that would make so mine is I think you're doing the correct. I think my suggestion is totally messed up.
I'm having trouble finding the flaw with your suggestion.
So the flaw with mine was it's actually not the 1 you should multiply stuff with. It's the other one. It is if females are smaller, then the minus something from the 1 should be minus more, and therefore you should only tackle. So the S should actually be in front of the EXP.
Yes, I think so. So I think what we're settling on is that there are multiple ways of solving this. One is tackling the actual mass thing right here, which comes in with the EXP, and the other one is just attacking it with the scaling factor that tries to relate mass to strength. Yeah. So I run this model exactly like it's set out here. Only I add a 1 to the PM value. And the reason I do this is just for interpretation's sake, and you'll see further down how we now interpret the PM coefficient. Because as we see PM down here, if I hadn't added the 1, this would have just been 1.667 or 1.67. And then this sentence would have just said that males are 167% as strong at maximum weight as their female counterparts. The way I've written it just now means that males are 0.67 times stronger.
Yeah, I think you should have written it with females being weaker, because otherwise you're leaking. Like now, phi is something weird because phi is multiplied by 1 point something when you're male.
I could have probably gone with an index solution rather than an indicator solution.
But it's not so much that. I think it's like,
what do you mean?
Again, I can be wrong here. I thought like phi was like this amalgamy of a bunch of different factors, and like one of the and the reason we have a 1 is because that's the maximum weight. And now implicitly the maximum weight is 1.6 because males are 1.6, right? So phi has to be sufficiently smaller for because the male part is now 1.6. So you're messing up your regression coefficients, right? Where since males are the larger, if being male meant that part of the thing in the parentheses summed to 1, then they would have the maximum weight. And since females are smaller, you should subtract something.
I see what you mean. Yes. Yes, I do see what you mean. But yeah, too late to change that now, eh?
No, yeah, and I don't think it's like,
yeah.
I don't fully understand what phi is, so like I don't know how devastating my critique is, but but let's just go on.
So how does this look when we plot it? This I've just shamelessly stolen directly from the solutions because I didn't feel like writing yet another ggplot solution. So basically, the black curve is the one for the males, the red curve is the one for the females. And we can see how males, just the older they get, with increasing weights, seeing how they get older. Again, everything levels out at around age 12. They just get much stronger with weights than the females do, hence why they crack more nuts.
This also explains, like, when you saw this the first time, right? Like the age 8 was super over dispersed in the original model, which kind of seemed weird. Because like the argument was they were adults, so they could, and like the guy who cracked the most nuts happens to be 8 years old, and there's also a guy, it's a girl I can see, who happens to crack 0 nuts, who's like 8 or 9, right? And now it makes perfect sense since the girl is smaller than the guy that all of these extreme outliers. Yeah.
It's also valuable to point out that females haven't been observed very often and not for very long. So there are not a lot of red dots, and most of the red circles are very small, except for one. So this female right here was observed for a long time. That's why it's got a big circle, but almost all of the other females weren't observed for any considerable amount of time.
Okay. So actually, the larger the circle, the more like that should. Like this, like if you actually made an over-dispersed curve, then that's like the large of the server, the large, like how large the circle is to go into predicting this over-dispersion, right?
Yes.
The only thing that's interesting is that all of the large circles seems to be outliers. Like the small circle seems to be closer to the regression line than the large circles.
Yeah, but I think that's randomness, to be honest. I don't think that's a model artifact.
No, I don't think it's a model. I think it's a data artifact. I think like I just a priori, right? If you record the data for like the monkeys for twice as long doing the nut thing, then most likely you would expect that it would regress towards the mean, right? Like if you only observed the monkey for 10 seconds and just had like a lucky streak. But it seems to be the opposite. And like maybe it's an like this is just like scattered galaxy brain. Like maybe it's because the monkeys were really good at opening nuts. They spent a lot of time doing it. They can observe them for longer time.
Yeah, I think this might also just be down to observer bias. because you will just
Oh, look at that guy, he's amazing.
Yeah, or just look at this one, she's so stupid she can't even open nuts, let's look at her for half an hour.
Yeah, like look until she opens a nut.
Yeah, no, as someone who's worked with primates before, that is exactly how you observe them. No, seriously, it's I had a few favorite monkeys who I would just look at over the entire day because they were just the cutest or the most stupid.
Yeah, okay. One thing though, like my critique of this that you should subtract it, right? The best thing about like you can construct these models how stupid you want. On the outcome scale, it doesn't matter, right? Yeah. It's only when you like if you want to interpret the regression coefficient, this matters a lot, right? Because like now you scale one of them by 1.6. But if you just want to look at the predictive distribution, then it doesn't matter.
Yeah. Yeah, this goes back all the way to first chapter about models can be mechanistically incorrect but predictively accurate. Moving on to practice question H2, we again are with the panda nut model, and now we incorporate individual differences. We've got two parameters, phi, which is the scaling parameter between mass and strength, and k, which is the density, which can both plausibly vary by individual. So an individual can really gain something from being heavy and in terms of strength. An individual can also be more dense than another. And I mean that both in the physical as well as the mental sense. We are supposed to pick one of these and allow that to vary by individual and use partial pooling to avoid overfitting. So we work with the same model that we've worked previously with, and then to incorporate the individual effects, we just need to add the data about the individuals to the data list and then incorporate that into the model. Now, in the model here, I'm just tackling phi again, because I've done that previously, so I could just copy and paste code down. And right here, we are adding a effect of individuals, and we're doing so in a non-centered way, hence why we're multiplying with tau right here for our Z ID. And that's all it is. We're doing this non-centered because the centered version just sampled really badly. So I just, instead of running a centered model just to show that it's bad, I just went with, okay, I saw this didn't work. Let me just right away report the non-centered version. And here's the model. I run the model like I set out to do up here, and I add the the JQ generated quantities portion to the code to just get the individual effect Z multiplied with the dispersion of it, tau. So this is just standardization, right? So this is just the standard deviation. I just multiply them back together again to get them back to the original scale of individual effect. That makes sense?
Yes. And you just picked an exponential just because it's easy.
Yeah, exactly.
Because like intuitively you want something symmetrical, right?
Yeah. Just because I didn't want to have to play around with prior predictive checks here.
I no hard feelings.
But thanks for asking me about it. So here's the precise output. Tau now just tells us whether there is differences between individuals, but it's difficult to interpret that one. So it's just, yes, there's a difference between individuals, but how do they look? So I just look at the precise outputs. With one would be painfully average individual, which individual 6 would be. And then we just have individuals which don't gain as much from weight in terms of what their strength ends up looking like. These are to the left-hand side here. On the right-hand side, these are the ones who gain more from being heavy in terms of strength as the others.
It would be fun to see like whether what gender these ones have, because like the whole like there are a lot of monkeys
yes,
where the male and the female has the same weight, but the female is like 8 years older, right? Mm-hmm. And are we then just like erroneously like all of the things that would actually be explained by age, but which our model is not able to do, is now actually, it comes back around in via this parameter.
Yes, we might actually just want to develop this model some more in future sessions. I think that might be quite interesting. Because yeah, I think we might find that to be the case.
Yeah, because it's the only way for the model to actually fit age.
Mm-hmm. Yeah, let's do that in a few weeks' time and just combine individual with
or just plot these ones in red and black depending on age, so you can just see if there's a bias.
You mean depending on sex?
Sex, depending on sex, yes. And then
yes.
Sex is a proxy for age.
Ooh, that's a good one. Yeah, definitely. I have no idea. I absolutely think there might be something at play here. I think that most of the ones to the right-hand side will probably be rather male than female. And yeah. I think including gender back into the model could flip this completely on its head.
Yeah, so wait. Okay, so if this number is high, that means it's doing better than the model would expect. So now it has this extra, like, it has this extra distribution where it can say, I'm in the tail because I'm awesome, right?
Yeah, and it basically means I'm heavy and I know how to make use of that.
Wait, does it say that?
Yeah, sorry, being to the right of this one means that you are better at leveraging strength from mass than the others.
Yeah, okay, so that means you're better than everybody else who has the same mass as you.
Yes.
And that's why I'm saying it means that you're female, because the females are like 4 years older and has the same mass.
Now I see what you're getting at. Ooh, yes.
So my guess is all the males sucks and all the females rocks, and it's an artifact of age.
Mm-hmm. Oh, that's a good one. Yeah, I'll definitely want to revisit that with you in future sessions. But for now, let's move on. But this is great. This is I was too busy just getting through this that I didn't stop to think about these things.
That's the huge advantage of doing nothing. Then you can just do only high-level thinking because you're not mucking around with the minutiae of getting it to run.
True. So H3, the chapter asserts that a typical geocentric time series model might be one that uses lag variables. Here you'll fit such a model and compare it to ODE model in the chapter. An autoregressive time series uses earlier values of the state variable, yada, yada, yada. Prepare the data, use this model right here, and compare that to the ODE model from the chapter. So I just quickly paste back in what the chapter did, and then quickly talk about the priors. There are no big revelations here, I'd say, in trying to get the auto.
Yeah, I know. We just debated this. And maybe I'm just not biological enough to think about this. But like if like all of the hares seem to die in the winter, and all of the lynx got fat because the hares were starving, so they couldn't run away. Couldn't there then, like if you actually had, every month these numbers, wouldn't it then, like the seasonality would actually be causally, that would actually be costly there, like indirectly in like X step back.
But it's still not the step itself that causes it.
No.
Yeah.
It's like it's only causally interpretable by we know it's winter, so we know they're starving, so we know they're easier to catch, right? So like if you had the variable winter, it would be causally affecting it. And this is a proxy for the variable winter, like 6 months ago.
I think what we're getting at here, which might make these models much better, is if we could vary our beta parameters, which is the effect of one on the other, by season.
Yes, definitely. And all I'm saying is that I think these steps that are more than one back, they may leak all kinds of interesting things like seasonality and gestation period. And if you don't have anything else, actually putting them in there, you could say they're causally interpreted as proxies for other things.
Yes, I'll give you that. Yes. But all of
I
that
was fishing,
information,
but
but all of that information still bleeds into just the previous time step.
yeah. The previous time step would be something else if they were not in winter like 6 months before. Yes, I totally grant you that.
Thank you.
But not the next time step. The next time step, because it's winter, we know that the rapid is going to run slower.
Yeah.
And we know that because there are like more rapids 6 months ago when there was summer and they were like doing the rapid thing.
Yeah, but I just.
No, I will. Let's table it because I think you are like the core argument that most of it goes through that last time point. That is like at least 95% true. And like whether there's some magical leakage that I can argue for in the other ones is totally up for debate.
Yeah, I think this is all about, it's not about, so this is the difference between what we just talked about, causally correct models versus predictively good models.
Yeah.
Because we can gain information from what was happening 6 months ago. But if we want to understand just the causal effect of population on itself, that's what was argued with the steps. Just population on itself, then the cause is never something that is further back than the last time step. There is information which you dubbed information leakage in what happened 6 months ago, but that will not be the causal effect of the population 6 months ago onto what's happening now. It will be all of the environmental stuff that is caught within what the population looked like 6 months ago.
Yeah, it's like that is definitely true. So
Yeah.
I think I'm only saying like you can argue it's causally because it leaks these other things that are constantly influencing. So because there's a correlation.
Yes, and I will say it's correlated, but not causally related. Because what you're doing is
I think that's yes, I think you're absolutely right.
The model doesn't give a shit. For the model, the information is there, but if we try to interpret it causally, that's where it falls apart.
Yeah. So I 90% agree with you, because like if you actually
I like your updating of your posterior belief there, by the way.
No, like, but if you actually made an intervention, right? And you had the causally correct model that only looks 1 step back, and the causally incorrect model that looks 12 steps back, and therefore can like infer that it was summer, even though it's not like causally it should be captured in only the last step. Then that model might actually be better at predicting the next step in the future when it doesn't know.
Yes, but that's always dependent on you hitting exactly the cyclicity of the underlying population, and that might not be in set intervals. It might be a moving window.
Time steps like a whole year back, then it will be there somewhere, right? Then the one 6 months ago, it happens to be the seasonality, right, or whatever. But I'm at least 90% with you.
Yeah, no, for me, I think it's become apparent that this is a disconnect between the causal interpretation of what we're looking at and the model predictive.
But I think there's two ways of defining causality, right? There's like the hardcore, this ball hits this ball, and therefore, and obviously,
yes, and that's the camp I'm in right now.
And in the predator prey thing, like you get eaten if you are there and the predator is there, and that depends on like these numbers. Like, no argument. But there's also like when you have observational studies, right? The whole idea is that you want to say what happens if I intervene here, and then you make some predictions. And if you do the kitchen sink approach and just put in all the variables, then all of the collider bias and all that stuff will mess you up, right? And I'm saying there's none of these collider biases or whatever when you actually take in these proxies for seasonality, such that like if you actually made a DAG. Then because T2 is before T1, so there's like so it's not, but it's so like the naive approach would be, well, it's blocked, right? But there's some path other, like not via T1 T2.
Yeah. Yes. So you're basically saying DAG wise we can have the causality of some environmental information of what happened 6 months ago flows somehow into what's happening right now. And we also just get rid of all of the post-treatment bias, which would be the next few time steps of the population.
Yeah, like my DAX looks like this. Here we have the current point. Then we have the 12 previous months. All those goes up to with an arrow which says, is it summer? And summer goes into how eatable are you? And therefore we don't have sure, it's a messed up DAX, but there is actually causal information flowing from summer to the animal. And from 12 months ago to summer, there's flowing causal information. And that's why in an intervention setting, my model would actually correctly predict the future without cheating.
And I 100% agree with you there. I think it's important that we highlight that we're talking about different causalities here.
Yeah. Perfect.
Oh, this is so
meta. This is so meta, this conversation. It's like, what is causality really? And the flow of information around a DAG. Who really cares?
Well, we do, obviously.
Loving it, guys.
No, I am. This is very mentally stimulating. I am liking this a lot.
Yeah, me too.
And I'm honestly looking forward to when we can do this, hopefully in person with a few beers. Also, I highly suggest that for once we're done with the study group, we keep this going, and we also pair future outings with beers.
Sounds good.
Fab. All right, but let's move on with this one right now. So for my betas right here, I just thought that the effect of hairs on hairs through the lag should be positive, but not always. So that's why I use a normal distribution. It is thinkable that if there are too many hairs, they will actually have a negative effect on the hair population size the next time step, because either they are overgrazing and then some starve, or because now the population is so big that it attracts a lot of lynx.
But is the model smart? Like the linear model is not smart enough to capture this, right?
No.
Like you also saw that from your prior picture where it just goes. So this like since you're always assuming a model, right? If you had these extra stats, like you had a regression coefficient for like hair squared, so that if there's sufficiently many hairs, it can go down. Then these arguments are good. But since the model can never capture this argument, I don't think it doesn't really matter.
Yes, this is what I meant by if we had a way of altering the beta coefficients by time. That would be great. Yeah, but unfortunately we just don't, and so I'm just going in with biological mindset, just thinking, well, it's probably positive, but it could also be negative sometimes. And that's why I just give this a normal distribution centered on one with relatively wide uncertainty.
I have a quick question.
Yeah, go ahead.
With these beta coefficients, we're talking about maybe if we added that time component, we could start talking about this, but would it also be easy to say alter them by n and have a density dependent effect?
Yes, that would be another one which would be highly interesting.
That might be a way around it.
It's going to be less hackiest, right? So like taking the number squared is the total hack GLM golem approach, and actually saying like I think like if there are more hairs than whatever per meter, because I talked to biologists, that seems like it's just too easy for the links. And then you could have like a sensible prior on that and actually make some informed.
I like it. I like it, guys.
Fab. I think that's mutual. Next coefficient, the effect of links on hairs. I say it's probably negative. Nothing more to add. They eat them.
I think that should maybe even be a lot.
I disagree. I disagree entirely. It will be a positive effect of links on hairs. I have no idea.
There's a 2.5% chance that it's positive, right? With that prior. Like this fat hair, it just needs to get in shape.
It will breed them to be stronger.
Exactly. Like
it has an evolutionary positive effect. Let's capture that in our time series model.
Yeah.
Oh my god.
All right. Next parameter that I'm looking at is the effect of links on links through time, and I'm assuming it has the exact same effect as hair on hair. Now for the effect of hairs on links, I assume that this is positive, and I just flip around.
Shouldn't you assume that like don't hairs get way more kids than links? So shouldn't you assume Like a large number for the hares and the.
I could, but this is not birth rates. This is just how much does population increase in so how much does population.
How is that not birth rate?
No, because we're looking at relative populations.
But that's still birth rate. So doubling, like if this is doubling and this is doubling, then that's the same birth rate.
Yeah, no. What I'm saying is, if you have, let's say we express our relative population as 100 as a scale of percentage. Let's say you are at 50% of carrying capacity or whatever have you, lynx population. Then I would affect that 50% lynx population to have as big an effect on increasing lynx population in the next time step as it would if these were hares.
Okay.
So the actual underlying numbers might be higher for the hares, and they definitely are, which also means that they birth more in the next time step. But the slope of this is the same for both species.
Okay, you're probably correct. There's just something about this model I don't fully get.
So the rate by which they grow by themselves, I have assumed to be the same, and we could definitely argue that hares grow quicker in population than lynx.
Yeah. Okay. Yeah, so it's one of these unidentifiable things where you just etch in some of the things. Yeah, perfect.
Yes. So I think your intuition is completely correct. It's just that we're not dealing with raw birth rate numbers.
Okay.
Fab. I run the model. I honestly already forgot what it actually was we were supposed to do. So let me just quickly look at this again. Just do the autoregressive model. Yes, that's what we were supposed to do. So this is just model from the book. And the data agree with my priors, which, no surprise. Hares have a positive effect on each other. Lynx have a positive effect on each other, and they actually agree with your intuition, where hares have a stronger effect on themselves, as lynx do on themselves.
Yeah, and it's not, and they're actually not quite narrow posteriors, right? They're not overlapping.
Mm-hmm. Lynx always have a negative effect on hares, and hares always have a positive effect on lynx. Exactly what we expect.
Yeah.
So what does the time series look like? Pretty garbage. That doesn't fit the data well. It just, I mean, maybe for hares a bit, but for lynx, which are shown in blue, nah. We're definitely missing something.
They're just not jumping high enough, right?
Mm-hmm. Exactly. So the model, what I thought might help here is now just add interaction effects to this. So try to add the effect of lynx. So sorry, for example, to predict hare population at the current time step. Let's try to understand that both through the lagged effect of hares on hares, but also through the effect of lynx on hares with the hare population times the lynx population. So now I added the lynx population to this. Sorry, the hare population. Because the effect, I argue, the effect of, and spoiler alert, this doesn't lead to anything. This was just what I was thinking. What I was thinking was the effect that lynx have on the hare population will be dependent on how big the lynx population is, but also how big the hare population is. So this is to go into the whole thing of, if the hare population is so tiny that the lynx can't find them, this could now pick up on that, is what I thought. I put this all into the model, and I mean, it does pick up on something, but now it just horribly overshoots.
It doesn't horribly overshoot, it just overshoots.
I mean, I'm not happy with how it's fitting over here.
It's not worse than the previous one, right?
It's not worse than the previous one, but this is still a model better than the previous one, but I'm not happy with it.
It's like, I think one thing that messes me up is like, when it's hares times lynx, it can't really shrink between there being twice as many hares or twice as many lynx, and that seems important.
Yeah.
Well, I obviously can't, right? Because the other regression coefficient is here by itself. Like maybe.
But yeah, this definitely needs more development, is all I'm saying. I wouldn't want to present this model to anyone except for study groups sessions. Like, you are worthy of my crap models. Take it. Now we go on to practice H4, which told us to adapt the autoregressive model from before with a two-step lag variable. So I just do the model from before, and I add the lag 2 to the lag 1. I run model without looking into the actual estimates here. Let's just look at the time series that get produced.
Yeah, it's also impossible to interpret the regression coefficient now that you have autocorrelation.
Yeah, still as crappy as the one where we had just a lag 1. This was the base model without interaction effects that now has lag 2 added to the lag 1 model.
Yeah.
This is no improvement at all. Now
Eric,
we do
you
the same.
keep insulting your graphs. That's all you end up doing. You just keep insulting your beautiful graphs.
Yeah. I learned I learned from McElry. Fuck the numbers. Look at the graphs.
Fair enough, fair enough.
No, it's just I think these are just very unwieldy, and also I will be honest, I just want to get done.
And just to touch on what Jan just said, I don't honestly understand when we get that many parameters coming out and the autoregressive stuff, it completely goes up. Like, usually you want to be able to, at least I want to be able to interpret what they actually mean. I don't really understand what these actually mean.
Well, it's just the sum of like the magic of 2 years ago and the magic of the previous one, right? And that's
Well, I mean,
hard to read about.
If we go into just one example here,
right
here, what the model thinks is that there is a strong positive effect of hairs in the previous time step onto hairs right now. And there's a positive but less strong effect of hairs 2 time steps away from now onto right now.
Right.
That's how we would read these two.
But it's like standard deviation of nearly 0.3, so it's a bit hard to say whether it's positive or, like, I don't know. I just find it a bit messy, you know.
I think this is all just about showing that adding previous lags to the model doesn't necessarily help.
Oh, overfitting for the win.
yeah, adding all of the lags helps.
All the lags. Give me 100.
Yeah, just full auto-regressive model, just all the way back to the beginning of time.
Sorry.
So now I do the same thing for the interaction model, which ends up looking a bit messy because we just now need to add so much stuff to it. I don't even look at the precise output anymore because this just gets
too many things
blown off the rails. And again, it doesn't really improve over the previous interaction model. I don't think that this added much to it.
Yeah, like I think what might help if you go back to the first model, like the very simple one, and just allow it to be over dispersed to begin with.
Yeah.
Because I think there's something that doesn't allow it to shoot up. So
there are definitely things that we might want to do to fix this. But again, this is just, I didn't want to end up with a perfect model.
If nothing else, if you make it over dispersed, some of the lines will shoot high enough up.
That's true. That's true.
And the main problem is that all of them are below, right? If some were above and some were below, but they were like way above and way below, it's actually better because at least it's capturing the fact that you're uncertain about the point.
Yeah, at least
now you're like confidently stating something wrong, and that's way worse than like not being confident in stating something.
Yeah. No, this is just subpar. So I also wrote down in my blog post that I reckon this exercise was just designed to highlight that higher order lags are a bit shitty and logical Volterra stuff doesn't always work. And I mean, at least base logical Volterra without any additions to it. And this comes in more and more importantly in this model right here, last exercise, where we basically do exactly what we've done for the Lynx hair model, just this time for mites. This time, because this is a strictly lab experiment where we could count everything correctly, we don't have any measurement error. So we don't need to account for that, which makes the model a tiny bit easier. And just looking at the data, we see here that open circles show the prey, closed circles show the predators. Yeah, looks like there's some cycles in here. Looks like one is tracking the other. Let's see if we can recreate that with a model. So I just quickly reestablish a simulation function according like I did with the links and hair function. I just now call it sim might. So we can run the simulation function that we used previously for links and hair for mites. Then I just play around with priors, not with any biological information because I know literally nothing about mites or their predators. So I just played around with the numbers until I landed on something that showed me at least some priors with some cycles in it. And then I just ran with those. Of course, I wouldn't want to do actual research like this because I want to have some proper prior information. But here, at least I know that I need to have cycles. And then I run a model, which I copied straight from the solutions because I wasn't confident in just coding up Stan myself. And basically, this is just the links model again, just without the measurement error. So all of this stays exactly the same as from links. You can actually see that all of the letters also in the solutions by McElridge stay the same. So it's still L and H for links and hair. And basically, it's just the model copied over, and I just updated the priors in it. That's all I had to do. And then we run the model, we get our output. Again, not looking into the parameters themselves, but just looking at the function, like, or the thingamajig, the time series that gets produced. And again, I'm not happy with that fit. I mean,
but this is the ODE model, right?
Yes. So quite clearly, this right here is not good for how it's fitting the predators. And this right here shows that we're definitely missing something for the prey. And some of the reasons that I'm seeing here why this might be an issue is that the way our model is built, the cycles are evenly spaced. And that might just not be the case in nature. The cycles might vary according to, and also in an experiment, might vary according to some additional covariates, which just are not factored into this very basic ODE approach.
I think the main problem here is this lab has a carrying capacity of 2000.
Mm-hmm.
So in this at week 20, the black one happens to hit peak carrying capacity and just stays there until the predators are caught up.
That's a good point too.
And we didn't have that issue with the real data because they were not close to carrying capacity. But like in a small environment, you hit carrying capacity much faster.
But I think this exercise was also just designed to show that Lotka Volterra needs modification to work properly.
But Lotka Volterra is just these ODE.
Yes, sorry, yes, Lotka Volterra is just the ecologists speak for ODE for predator and prey.
Yeah, but like if you just make like an ODE for it with itself, just that it can when there are many of them, it can be bad for itself and it can be bad for because obviously the more there are, the more the links will eat. That's a given, right? But if the more there are, the more they will die. There will be some number they never get above. If every hair kills 0.1% hair, there'll never be more than 100 hairs. Right? So if you just have that as part of your ODE, it could predict that it flatlines at 2000.
Yes, that's exactly what I'm saying. We need modification for this to work properly. Yes.
Eric, you were making an assumption about maybe some parameters, some predictors are not involved in the model. That's why but I didn't get that part. Can you please re-explain?
Sorry, come again? The last part?
You're cutting out. You're cutting out. You're
muted yourself.
Okay, so you were talking about this kind of shape can be resorted to if some predictors were not inputted in. So I don't get the relationship with that. Can you re-explain that part, please?
Yeah, of course. So this predator-prey dynamic is resolved to a certain degree. But I would argue that even in a lab setup, there are probably additional covariates which influence how fast a population grows or declines. And having these in the model, so like the carrying capacity that Jan just mentioned, might have made the model much more realistic and more accurate.
If the grad students only get 2 kilos of food, and 2 kilos of food is only enough for 2,000 rodents, then that perfectly explains why it never goes above that, because that's how much food the grad students put in every day when they do the experiment, right?
Okay.
Did that help?
Yeah.
Cool.
Yeah.
All right. With that, we've actually reached the end of this. And I'm legitimately happy to be done with these exercises because they have been a terrifying time sink, but also really fun to solve. So it's a bit bittersweet, but I am ultimately happy that I'm done.
Yeah, you've gotten smarter, right? That's the important part.
Oh yeah, leagues and bounds. No, I'm not saying I'm smart now. I'm just saying I have gotten smarter.
Yeah.
All right, guys.
Yeah.
I think this is where we'll end this for the day.
Yeah.
And I'm looking forward to seeing all of you next week. Again, if you have additional things that should be brought up next week, please send them to me. Also, if you have the time to just put together a super quick thing of what do you plan to do with the kind of things that we've talked about, that'd be dope. And yeah, next week's going to be pretty nice, I think. Got some cool stuff prepared already. And I'm looking forward to seeing all of you.
Sounds good.
Bye.
See you next week. Bye.
See you
Bye.
guys.